Piggybacking on millions of years of evolution we've undergone to process spatial relationships, the human retina can transmit about as much information to your brain as a broadband connection does to your computer, which means our eyes and brains combined are incredible information processing machines. That's part of why we can often understand things more quickly by looking at a representation of data than by racking our brains over long lists of raw digits. Pictures and graphs can help us make sense about huge amounts of numbers that would otherwise be well beyond our capacity. And the way we get into that deeper meaning behind data is by creating data visualizations. You might have heard the phrase, "a picture is worth 1,000 words." And in math, we can go even further. I'm Jason Guglielmo, and this is Study Hall Real World College Math. In this episode, we'll build on what we learned about sets and probability as we start our new unit on statistics. Statistics is all about analyzing data of some kind to make sense of it in an organized and structured way. And in the real world, when it comes to statistics, whatever we're studying involves looking at a big collection of things. Like, we might want to know what proportion of people visiting an online store use a discount code, or the fraction of alternators made in a car manufacturing plant that are faulty, or even how many stray cats wandering a city might be carrying fleas. In each case, we have a big collection of some particular thing we want to know more about, which we call a population. Depending on what we're studying, we might mean a population of people, but we can also talk about the population of books published last year, or even the population made up of Harry Styles' tweets. Now, ideally, we'd have data on every member of a population we're interested in, but normally that's not the case because it's not always practical, affordable, ethical, or even possible to collect it all. Instead, we're usually working with data from a sample of the population, which is a smaller subset of it. If our sample is representative, which we could fill an entire episode talking about how to make sure a sample accurately reflects the population, so definitely dig in if you're interested, we can then study the characteristics of the sample to get an idea of what the whole population is like. At any rate, whether we have information about a whole population or just a sample, usually we're going to end up with a list of data. The specific feature we're collecting data on is called a variable, like whether or not a plant is healthy, or the size of an asteroid, because it's something that can vary across our data. That's usually why we want data on it in the first place. The fact that whatever we're studying is different between different bits of the population is what makes it interesting. To learn more about variables and how we might visualize data to make sense of them, let's head to Alice and Blake, two civil engineers. The city Alice and Blake work for is investigating flooding risks in the suburbs. Specifically, Alice and Blake have been tasked with investigating how people's front yards may or may not be contributing to flood risks in their neighborhoods. See, big paved driveways cause water to run off into other areas, rather than being absorbed into the ground. But a grassy lawn with sandy soil will absorb the water really well, and a clay soil will do an okay job. Broadly speaking, the greater the area of paved surfaces, the greater the potential flood risks to a given neighborhood. So, with permission from some of the residents, Alice decides to conduct a survey of 1,000 random lawns across different suburbs around the city, measuring how big they are and whether they're paved. As she's traveling all over the city collecting this data, she periodically sends some back to Blake in the office. By the time he's received data on a few dozen front yards, Blake wants to start getting an idea of what the distribution of yard sizes looks like, or the range of yard sizes and how often a certain kind of yard exists within the sample. He pulls up the numbers in his favorite spreadsheet program, which is how lots of people tinker with data and can also be used to produce all the different kinds of data visualizations we'll be talking about in this episode. In the data Alice sent over, one column has all the yard areas she measured in thousands of square feet, which is basically just a long list of numbers. When we have a whole bunch of numbers like this that aren't organized in some way, we call it ungrouped data. And the fact that our data takes on the form of a number makes it a quantitative variable, which is just math speak for saying the variable is a quantity of some kind. In this case, the size of a yard. Since so far Blake's only dealing with a few dozen numbers or so, one way to check out all of the actual data points is using what's called a stem and leaf diagram. This is the first data visualization we're going to cover. First up, we sort all of the data from smallest to largest. Then, the stem is a column of digits from smallest to largest, representing the tens column of a particular number. So 1 is 10, 2 is 20, and so on. The leaf column has the second digits of all of our numbers, or the units column of the particular numbers, like the 2 in 62. Or the 9 in 49. The leaves go on the corresponding row of the stem, depending on the original data point. Like to record the yard that's 42,000 square feet, we'd add a 2 in the row of the stem corresponding to 4. And just to make that super clear, we also include a little key in the diagram with an example of how to read off a number from the stem and leaf and what it means. Now, as ungrouped data, those numbers didn't easily tell us much, but as a stem and leaf diagram, we immediately see some patterns. The advantage of all this is we can keep all the information about individual data points readily available while getting an idea of the shape of our distribution of numbers. Of course, this shape is just one possibility for the kind of distribution we might encounter. So to compare, Blake also requests some similar data for comparison from his colleague Celestina, who works in a different city. There's a whole side of our stem in our diagram that's unused, and with the exact same logic, we can include the yard data from the other city. The leaves may be on the left, but we still read each data point starting with the stem and going out to each leaf. We can see in the other city there's way more small front yards. The distributions between the two cities are different, which tells Blake that whatever conclusions he draws, he can't necessarily apply them to other places. Now, while Blake tinkers with some preliminary data, Alice finishes collecting data on all 1,000 properties and heads back to get a closer look at the full sample. As well as the size of the yards, Alice collected data on whether they're totally paved over, if they're a mixture of lawns and paving, if they're mostly lawns with clay soil, which absorbs a little water, or if they're mostly lawns with loose, sandy soils which absorb lots of water. Notice that these aren't numbers, but are instead different categories that the variable falls into, which is why we call this kind a categorical variable. What's more, since the data itself is nicely grouped in these distinct categories, it's also called, you guessed it, grouped data. So now Alice wants an idea of how often each category comes up in her sample data, and she can visualize the frequency of each category in her data using the same spreadsheet program as Blake to come up with a table. Tables are handy and definitely earn their own place as a data visualization tool, but sometimes to really get a sense of the difference between the numbers in a table and easily scan for any interesting discrepancies, outliers, or patterns, it helps to make a table's information more visual. The way we typically do that when dealing with categorical data is using what's called a bar graph. Every bar graph has an axis, normally the horizontal one, where each of our different categories has its own space. It also has another axis, usually the vertical one, which is a scale for the thing we're interested in. In this case, we're interested in how frequently each category occurred in the sample survey. We then plot the values for each category with a bar and leave a little gap to distinguish each bar. At a glance, Alice sees that only about a quarter of the yards in her sample are totally paved over, so all the other yards have some drainage capacity. But the lawns with sandy soils only make up about a fifth of her 1,000 data point sample. Blake, meanwhile, is still interested in the distribution of the size of yards now that Alice has brought back a full 1,000 yard sample. With so much more data, this time he decides to use a histogram. We can think of a histogram as a special kind of bar graph that shows how often quantitative data falls into different snippets of the overall range. Let's go back to Blake's long list of numbers representing the area of yards. Only now he has 1,000 rows. Taking ungrouped data and putting it into groups involves what we call binning, which means dividing up the full range of the numbers into smaller chunks or bins. For instance, he might decide to create bins that each represent 10,000 square feet. So 0 to 10 is the first bin, 10 to 20 is another bin, 20 to 30 is a bin, and so on. Blake can then look at the frequency of his data by seeing how many data points fall in each bin. Like the data point 32 falls into the bin whose boundary is 30 and 40. With all 1,000 data points and his histogram, Blake can see that the yard areas fall into a kind of bell-shaped distribution across the bins, centered at around 60,000 square feet or so, with a lot of yards being somewhere in the ballpark of 40 to 80,000 square feet. Finally, back with Alice, she realizes that her supervisors will be interested in how her sample has been put together from different suburbs across the city. They'll want to see if the data represents the whole city or just specific slices. Incredibly conveniently, the city has 5 districts named District 1, 2, 3, 4, and 5, which are about equal in size, and Alice recorded which district each yard comes from. So again, Alice is working with a categorical variable and group data about the different districts. Much like before, she wants the frequency of each of the districts in her sample, but this time as a proportion of the whole. That's because the absolute number of data points belonging to a district isn't as interesting as how much of the whole sample comes from each district. So in this case, she figures a pie chart will do the trick. Pie charts are circular charts, where each slice of the pie has an area which is proportional to how often each category shows up in the data, and gets a label corresponding to the category it belongs to. She calculates what's called the relative frequency by dividing the frequencies of each district by the total number of data points in her sample, 1,000, and turning them into percentages in her spreadsheet software to get a table. And this table of relative frequencies is what she turns into a pie chart. So the slice corresponding to District 1, which makes up 30% of her sample, corresponds to 30% of the chart. Pretty neat. At a glance, Alice and her supervisors can spot that Districts 2, 3, and 5 don't have quite as much data as the others, and it might be worth surveying a few hundred more yards there to even out the sample. At this stage in their process, Alice and Blake have lots more to do in putting together a full picture of the yards and their contributions to flood risks in each district. But even at these early stages, the visualizations helped make quick work out of hundreds of data points to make sense of them. And that's one of the most important ideas when it comes to dealing with data, especially huge amounts of it. While we might not be able to draw quick, sensible, and helpful conclusions from long reams of data, we can make sense of them in other ways. More generally, when facing lots of data and an important question about the world, the way we learn and draw actual, meaningful, and understandable conclusions is by using math to apply some kind of process to the data, or summarizing it to bring it down to a scale our minds can deal with. And exactly how we might summarize our data is what we'll be looking at next episode. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you liked the video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.